Okay, so now case number 3 is basically k belongs to this interval 0 to 1, right? So case number 3 is basically k belongs to this interval 0 to 1, and that basically means that basically the output of the function is equal to 0, right? So here basically f of x is equal to 0. So since this is an interval, I can write basically f of k is equal to 0, and also the limit of f of x as x tends to k is equal to the limit of 0 as x tends to k, which is equal to 0. And therefore f of k is equal to the limit of f of x as x tends to k is equal to 0, and therefore f is continuous at basically for all k belonging to this interval here, belonging to the interval 0 to 1. So that's the next part. Now case number 4 is k is equal to 1, and when k is equal to 1, that means that the output of the function is still at 0, right? So, and that is where basically the function is of course not continuous. So that is case number 4. And that is when k is equal to 1, and here f of x is equal to 0. Okay, so case number 4, k is equal to 1. Okay, so now basically over here we can say that over here f of k is equal to basically 0. Particularly you can write f of 1 is equal to 0. Now this is a point, so the limit of f of x as x tends to 1 from the right, you have to be looking for some numbers greater than 1. So that is equal to the limit of some numbers greater than 1 would be this part of the function, which where the value of the function becomes 4x. So that's the limit of 4x as x tends to 1 from the right, which is equal to the limit of basically 4x as x tends to 1, and that's equal to 4 times 1, which is equal to 4. And the limit of f of x as x tends to 1 from the left, you have to be looking for some values for less than 1, and for less than 1 you have to be looking at this part over here where the output becomes 0, right? So you have the limit of 0 as x tends to 1 from the left, which is equal to the limit of 0 as x tends to 1, right? And that is equal to 0. And therefore the limit of f of x as x tends to 1 from the right is not equal to the limit of f of x as x tends to 1 from the left, and that means that basically means that the limit of f of x as x tends to 1 does not exist. And since that is the case, you can say that f is not continuous at k is equal to 1, or at x is equal to 1. And of course you can see that over here that that basically the function jumps from here, jumps up, so of course the function is not continuous here. And of course you know that basically this point x is equal to 1 is a part of the domain of the function. If the point was not a member of the domain of the function, of course this wouldn't be a problem, but since it's a member of the domain of the function, then you can say that the function is not continuous here. And then we have case number 5, where k is greater than 1. We have case number 5. You have case number 5 where k is greater than 1. When k is greater than 1, of course you can see that basically you have to take this, the output of the function becomes 4x. This is f of x is equal to 4x. So basically f of k over here would be equal to 4k. And the limit of f of x as x tends to k would be equal to the limit of basically 4x as x tends to k, which is equal to 4 times k, which is equal to 4 times k, which is equal to 4k. And since these two are the same, have the same values, meaning that since f of k is equal to the limit of f of x as x tends to k is equal to 4k, therefore you can say that basically f is continuous for every k belonging to, for every k greater than 1. And therefore basically the only point of discontinuity, the only point of discontinuity of f is basically x is equal to 1. Is x is equal to 1, and that is basically the answer here. Now you can see that of course each of these problems is important and has to be taken care of. You do not want to leave any of these out. At least once you have to do them. Sometimes you have to do them more than once, but hopefully not. So the next question is question number 16. Exercise number 16, which is basically, again, you want to discuss the continuity of the function f of x is equal to -2 for if x is less than or equal to -1, or it is 2x if -1 is less than x is less than or equal to 1, and it's equal to 2 if x is greater than 1. If x is greater than 1, right? So how would you solve this problem? First you have to draw the graph, because I would probably get lost in the numbers and in the algebra here. Doesn't really work for me too well. I have to see a picture. So now if f of x is equal to -2, I'm going to basically write this in -2, and then basically the function would be this way. And of course this is for x is less than or equal to -1, meaning that this is -1, and therefore the function becomes something like this. And and then this part is just not, and then of course this part over here is, this is -1, this is -2, and of course this part is not a part of the function, so you want to be aware of that. This is -1. So this is the function. So you can see that for x is less than or equal to -1, and of course you can see that when we say equal to -1, then this becomes a filled circle, meaning that at -1, this filled circle is the output of the function, and the output of the function becomes -2, right? Now for basically f of x is equal to 2x, if x is between -1 and 1, so between -1 and 1 you have basically, this is 1 over here, and 2x would be a line that goes through the origin having a slope 2. So this is 1 and this is 1 and 2, and so the line goes through these 2 points, and of course it has to come over here. So, and you see you have a filled circle over here above 1, you have a filled circle over here, you have a hollow circle, and that is basically your function between -1 and 1. And for x is greater than 1, the output of the function is 2. It's actually an interesting function. The output of the function is 2, meaning that this is 2, this over here is 2, so you will get basically a hollow circle here, and then this is a line that goes all the way up to here. This is actually an interesting function. So you can see that the function is actually continuous. There is no problem with the function. Now if I say that, for example, let some k belong to the set of real numbers, then I can consider some case 1 where basically k is less than -1. Then I can consider some case 2 where my k is equal to -1. Then I can consider some case 3 where my k is basically between -1 and 1, belongs to -1, 1. And I can consider some case 4 where my k is equal to 1. And I can consider some case number 5 where my k is greater than 1. And when I do so, I have gotten myself a whole lot of work to do. So let's see. Okay, so now basically we have these 5 cases that we need to take a look at. So first of all, let's take the case number 1 where k is less than -1. So case number 1 where k is less than -1, and when k is less than -1, the output of the function is -2. So over here f of x is equal to -2. So which means that basically f of k would be equal to basically, well, simply -2, and that's basically the end of the story. Now, and this happens because of course it's a constant function, otherwise you wouldn't get, it's constant over here. And the limit of f of x as x tends to k is equal to the limit of -2 as x tends to k, and that is equal to -2, right? And I think it's time. I mean, I could actually talk a little bit about, at least over here, I can explain these limits a little bit, so that because I am pretty sure that many people have a lot of misunderstanding or problems with limits, because limits are, it's a very simple thing, but nonetheless it's very, sometimes it can be very confusing. So you see over here, basically what I'm saying is that basically k is less than -1, this case over here, and when k is less than -1, then of course I will come up with this part of the function, which is essentially this line over here, and the output of the function, you can see that it's a constant horizontal line which is at -2, so the output of the function is always at -2, right? Now so of course it makes sense that now, since k is any value less than -1, so you can see that when k is, which is the input of the function, is any value less than -1, so that means that any value less than -1, if I enter into this function, the function is of course always going to give me the same value, -2, because the value of the function does not depend on x. It's just a constant number. It doesn't change. Whatever you want to input here, the output does not change, and that is generally meant by a constant function. A constant function basically doesn't change, right? And of course the slope of this line is actually equal to 0. Since the slope is 0, the value of the function is not changing, right? Now so you understand, of course, this part over here, which means that f of k is equal to -2. So this makes sense. Now when I say the limit of f of x as x tends to k, what this means is that basically you can, for all intents and purposes, for this part, you can of course imagine that we are talking about all of these numbers less than -1, because we have basically set the condition here that x is less than -1. Now since x is less than -1, you can of course imagine that we are talking about all of these x's over here, and for those x's, basically the value of the function, as you can see, is equal to -2, right? And when I say the limit of f of x as x tends to k, that means that the limit of f of x, I can for example say the limit of f of x in this particular, basically over here in this particular case, I can say that the limit of f of x as x tends to, for example, -2, right? As x tends to -2, and then I would have this point over here -2, and I would have this point over here -2 over here, right? And then you can see that basically the limit of f of x as x tends to -2, of course you know that what this means is that basically the limit of f of x as x tends to -2 is defined if the limit of f of x as x tends to -2 from the right is equal to the limit of f of x as x tends to -2 from the left, right? So that means that you go around -2, you go around this point over here, and then you have to get closer and closer to -2 from from the left and from the right as well, and note down what is the values of the function for each of those inputs, meaning that, for example, in this particular case, what I have is that basically let's take into consideration basically this part of this equation. So the limit of f of x as x tends to -2 from the right means that basically I consider some values very close to -2 but larger than -2, because here I'm saying that tending to -2 from the right, meaning that I'm approaching -2 from the right from this side. So of course these values would be greater than -2. So then I can basically imagine some values, for example, -1.9. And again, I can get a little bit closer, for example, -1.99. I can get a little bit closer, -1.999, and so on and so forth, right? Now, what is the value of the function if the input is -1.99? If the input is -1.99, you can see that the output is -2, right? So the output is -2. If the input becomes -1.99 over here, somewhere over here, the output is still -2. And again, for this input, the output is again -2. So that means that basically if I have the point basically -2 over here, and if I approach it from the right, which is basically what I'm doing over here, and please note that basically -1.9 is a little bit, there is 1/10 of a unit difference between these two numbers. Then there is 1/100th of a unit difference between these two numbers. There is 1/1000th of a unit difference between these two numbers, meaning that as I'm moving in this direction, I'm actually getting closer and closer to -2, of course, from the right. Okay, so what this means is that as I'm getting closer and closer to -2, of course, in this particular case, the value of the function is remaining the same. But usually what happens is that the value of the function gets closer and closer to some particular value, right? That particular value would be the limit of the function at that point. And this situation over here, I can write it as limit of f of x as x tends to -2 from the right is equal to -2, right? Is equal to -2. And by the same logic, then what you can do is that you can do the same thing for this part of this equation, meaning that you can basically come over here and get closer to -2 from the left. Getting closer to -2 from the left, that means that you have to enter some values into the function which are a little bit smaller than -2, because as you move towards the negative x's, of course, the value of numbers gets smaller and smaller and smaller. So that means that basically then you have 2.1, right? -2.1. So you can try -2.1. If I were to get a little bit closer to 2 from the left, I would try 2.01. If I were to get a little bit closer to -2, I would try 2.001, and so on and so forth. And as you can see, as I'm moving towards -2 from the left, basically the difference between these two numbers is 1/10 of a unit. The difference between these two numbers is 1/100th of a unit. The difference between these two numbers is 1/1000th of a unit, meaning that as I'm moving basically in these numbers, the distance between each of these numbers and -2 is getting smaller and smaller and smaller, meaning that I'm getting closer and closer to -2 from the left, right? And of course, you know that basically this function is built in such a way that you have this situation going on from negative. Basically, you have this situation going on. You have this constant function like this, and whether I input this value into the function or input this value into the function or input this value, the value of the function is always at -2, which means that over here you have -2, -2, and -2. And since as I'm getting closer and closer to -2, the value of the function is, let's say it's getting closer and closer and closer to -2 here, then you can say that the limit of f of x, if I call this function f of x, the limit of f of x as x tends to -2 from the left is equal to -2. That is the meaning of a limit, right? So if you understand this much about limits, then of course you will be able to understand the meaning of each of these steps, and you will of course be able to write these on yourself, and you wouldn't have any problem. So that's basically the meaning of a limit. Or for example, to give you another example so that you understand the meaning of a limit, is, for example, suppose that you have this function over here 1 2 3 4 1 2 3 4, and so you have 1 and 2 comma 4 and this value over here and this value over here, and suppose that you have this function over here. Suppose that you have this function over here. Suppose that this is f of x is equal to x squared, and suppose that this is 1 comma 1, and suppose that this point is 2 comma 4. Suppose that this point is -1 comma 1, and suppose that this point over here is -2 comma 4, right? This is a simple function f of x is equal to x squared. Now I can calculate the limit of this function at any point, right? I can say that, for example, I can calculate the limit of this function as x tends to 2, for example, meaning that at x is equal to 2, I can get closer and closer to 2 from the right, right? From the right. So if I want to get closer to 2, I would try, for example, 2.1. Then I would try, for example, 2.01. Then I would try 2.001. As you can see, as I'm going through these numbers, the numbers are getting closer and closer to 2, from the right, right? The numbers are getting closer and closer to 2 from the right. And so I can simply calculate these outputs using a calculator. This function is a squaring function, meaning that if I give it 2.1 and raise it to the second power, it gives me 4.41. If I give it 2.01, raise it to the second power, it will give me this value, whatever that is. 2.001 raised to the second power, it will give me this value over here, right? So now I will write down these values over here for this value, for this input. Suppose that this is x and this is f of x. For this x, I'm getting 4.41. For this x, I'm getting 4.01, 4.040, sorry. I'm getting 4.0401, and for this value, I'm getting 4.004001, and suppose that I just keep going in this direction and get very, very close to 2, meaning that I try, for example, 2.000000001, meaning that I have 8 zeros over here, right? And this would be basically 2.000000001 raised to the second power. That gives me basically 4.000000004, right? So as you can see, as I'm getting basically closer and closer to 2 from the right, the values of the function is over here is 4.4. The value of the function over here becomes 4.04. It's moving, as you can see, it's moving towards 4. Over here it's become 4.004, again closer to 4. And over here you have 4.00804, meaning that it's almost 4, right? And of course, from this function, you know that f of 2, meaning that if I enter exactly 2 into this function, exactly 2, that gives me 2 to 2 raised to the second power, which is equal to 4, right? So in this situation, I can simply write it as the limit of basically f of x, the limit of f of x as x tends to 2 from the right is equal to 4. It's very simple, right? And by the same logic, what I can do is that I can basically now get closer to 2 from the other side as well, from this side. Meaning that from this side I have, for example, I could enter, for example, 1.9. I could enter 1.99. I could enter 1.999. I could enter 1.9999 and just keep going 1.999999, for example, 99, and so on and so forth, and see what sort of outputs I'm going to get for these numbers. So the outputs basically that would be, for example, 1.9 squared would be 3.61, 1.99 squared would be 3.9601, 3.9601, and 1.999 raised to the second power is 3.99601. And if I enter this number over here, suppose that I enter 1.24679, for example, 24679, I will get what is that? I didn't raise it to the second power. So that would be 6 nines and 6. So this would give me 3.999999 and a 6. So you can see that the value of the function over here is 3.6 for this input. The value becomes 3.96, then becomes 3.99, and this becomes 3.999999, and so on and so forth. And of course, we know that if we input 2 into this function, of course, sometimes it's not possible to do this part. This one, it's not possible to do it because, for example, for whatever reason, the function is not defined at x is equal to 2. And that's basically why the limit has been built, because the function is not defined at x is equal to 2. And so now you want to know what would be the value of this function if this function was defined at x is equal to 2. What sort of value would it give you, right? So that's basically why limit has been built in the first place. It has been built for derivatives, and it was built for physics, because physics wanted to know the instantaneous velocity. Instantaneous velocity is the exact same function, but the problem over there is that this particular function is not defined at x is equal to 2 over there, because you want to calculate the average, the instantaneous velocity. Basically, when you calculate instantaneous velocity, you go 0 distance and 0 time has passed, so you're dividing 0 by 0, so your function is not defined over there, right? And so there is no way to enter, for example, 2 into the function and get a 4 from it. The function doesn't work over there. It becomes an indeterminate case, right? So basically now I can see that. So essentially this is not available to you most of the time, at least. I mean, if it was available to you, there would be no point in doing all of this calculation. You would just simply enter 2 and you would get a 4 over here, right? So basically then what this means is that, so you can see that the values of the function are getting closer and closer to 4. So this situation, I can write it as the limit of f of x as x tends to 2 from the left. You can see from the left is equal to 4. Now, since the limit of f of x as x tends to 2 from the right and from the left, both of them, is equal to the same value, therefore, you can say that the limit of the function exists, and you can call it the limit of f of x as x tends to 2 is equal to 4. And then, well, by the same logic, for example, you can say that the limit of this exact same function, the limit of this function, for example, you can say that basically the limit of this function at as x tends to 0 is equal to 0. It's the value of the function at x is equal to 0. The limit of f of x as x tends to 1 is equal to 1. It's the value of the function at x is equal to 1. The limit of f of x as x tends to negative 2 is equal to 4. It's the value of the function at that point, and so on and so forth. Of course, it's not always, I mean, the value of the function is always not available to you. But that's basically the idea of limit. And this is one of the most important things in mathematics. Must be understood properly. Very simple idea, but extremely powerful. Extremely powerful. So I will I take a few minutes rest, and we will continue with this exercise. Okay, so now that hopefully we understand more about basically all of these things about limits, let's continue with this exercise. So now basically what we need to do is case 1, which is basically case 1 over here, which is k is less than 1, k is less than negative 1, and you can see that f of x is equal to negative 2 here when k is less than negative 1. And so basically, if any k that I choose here from all of these k's less than negative 1, then the output of the function, of course, as you can see, is going to be equal to negative 2. That's basically why I write f of k is equal to negative 2. Otherwise, there is no other reason for me to do that. And moreover, now I need to basically, that basically means that for this basically means that for every k belonging to this interval from -2 all the way up to -infinity, or from -infinity all the way up to -2, I know the value of the function is -2, right? So that's what I wanted to do here. Moreover, I need to make sure that the value of this function all throughout this interval from -infinity to -2 is the value of the function is equal to the limit of the function at each of those points, meaning that any point that I take here, the value of the function has to be equal to the limit of the function at that point. Again, I need to make sure that the next point, again, the same thing applies, the next point, the same thing applies, and so on and so forth, all throughout this domain, right? Now, this necessarily doesn't have to be something like this. This could simply be, for example, some function like this. For example, all the way up to -1, all the way up to -1, suppose that I have some function that is basically something like this. So this is not a constant function, this is constantly changing, or even something like this, and so on and so forth. So again, I need to make sure that if I take this point over here, now this is -infinity, this is -1. I need to make sure that as I start from -infinity and go all the way up to -1, so for example, suppose that I pick this point, call it x1. At x1, this is the output of the function. This point is f of x1. And of course, the function has some limit at this point, meaning that I know that f of x1, meaning that I know that at x1, the output is equal to f of x1, right? Now, at x1, what is the limit of this function? Meaning that if I get closer and closer to x1 from the right, and if I get closer and closer to x1 from the left, meaning that if I get closer and closer to x1 from the right, limit of f of x as I get closer and closer to x1 from the right, that is equal to some value, right? Some value, meaning that this would be this value over here. That is, let's call it m, for example. And as I get closer and closer to x1 from the left, from this side, the limit of f of x, the limit of f of x as x tends to x1 from the left, there again you will get some value over here. This value, let's call it n. If these two values, if m is equal to n, then basically you can say that the limit of it's called, of course I have to, well, that's okay. Then I can say that the limit of f of x as x tends to x1 is equal to either m or is equal to n, doesn't really matter. You can choose one variable. And moreover, if basically if m is equal to n is equal to the output of the function at that point is equal to f of x1, then that simply means that the function is not broken here. Otherwise, the function would look something like this, for example. It would look something like, for example, it would come over here, and then there would be something like this, and going in this direction. So you can see that over here, the value of f of x1 is this value over here. This is f of x1, and let's call this, for example, x1. And this would be this value also would be this value would also would be the limit of f of x as x tends to x1 from the left, and this value would be f of the limit of f of x as x tends to x1 from the right. And you can see that these two are not the same, and therefore the function is broken, right? So now this condition has to apply to each and every point in the domain of the function for every x1, and now this x1 we have called it k over here, and we have to make sure that for every k, if I basically find the value of the output of the function, which is this value over here, call it y1, this is equal to the left hand limit of the function at x1, and is equal to the right hand limit of the function at x1, meaning that the function joins together at that point, and also it's equal to the output of the function. And if that's the case, then that means that basically your function is basically continuous. So, and this has to apply to each and every point in the domain of the function, right? In the domain of the function. Of course, there is one consideration here, which is what I'm thinking about. Maybe I will leave this thought to you. You need to figure out why the common limit is supposed to be equal to the output of the function at that point, which is something to think about. You can think about that and tell me why the common limit has to be equal to the output of the function at that point. The condition is set this way, but why that is, that you can tell me. And I will think about that as well. So basically now what I have done here is that I know that the value of the output of the function at every point for this function f of x, I know the output of the function at every point is equal to -2. And then I need to make sure that the left-hand limit of the function at exactly at that point is equal to the right-hand limit of the function exactly at that point, and these three values are equal. And if that's and since I've chosen some k arbitrarily from that belongs to this interval from -infinity to -1, then if this condition is fulfilled for k, that means that basically then this condition is fulfilled for every number that belongs to basically this interval from -infinity to -1, and that means that the function is simply continuous for every number from -infinity to -1, right? So it's a very simple idea, and of course checking this otherwise would be simply impossible, meaning that the algebra and logic are basically working together to do something for you which would otherwise be simply impossible, meaning that you couldn't possibly sit and check this condition for any function. It would take you a lifetime to do that. Even in a lifetime you wouldn't be able to do that, because the number of real numbers is infinite. Even if you want to check the function, for example, not from -infinity all the way up to +infinity, even if you want to check this condition from -2 to -1, even between these two numbers, between these two numbers, you would be able to find an infinite number of real numbers, and therefore it would be impossible for you to check this condition even in 10 lifetimes, right? So basically you can actually say with absolute certainty that and I have always said this, that algebra is actually something it is something actually alive. It's not something dead, or it's not that dry logic. It's actually alive, that it's a force that works in our that actually works in our universe. And it's not like, for example, we have invented algebra, as many people might believe, meaning that I think it would actually be right to say that algebra is something alive, and we have only discovered it. It's not that we have basically we have invented it in any way, because such things you cannot really invent. You can invent an airplane, you can invent a computer, you can invent a audio system, you can invent a cup, you can invent paper. All of these you can invent, but algebra by nature cannot be invented. It's a very specific type of system. Okay, so now basically now I know that the limit of f of x as x tends to k. So basically I know that the f of x, since f of x is equal to -2, I can write this as the limit of -2 as x tends to k, right? And since -2, since the function is basically a constant function, it doesn't matter what values of k you have here, the function is always giving you the output -2. Therefore the limit of -2 as x tends to k is equal to -2. Whatever k might be, your limit would be equal to -2, right? And that is basically that, and that basically shows that at any point k belonging to this interval from -infinity to -1, any point that you take in the domain of the function, the value of the function, which is equal to -2, is equal to the limit of the function at that point, which is again equal to -2, and therefore the function is continuous from -infinity to -1, right? So that's basically the whole idea here. If you understand this, the logic behind this, then the rest is just working with limits and just simple algebra. Otherwise, there is not much going on here, and the whole of calculus is just this simple idea that you have only three simple ideas. There is the limit, there is the derivative, then there is the integral, and these are and if you really think about it, the derivative is just not, you cannot really call it an idea. The main credit goes to limit, and the integral is just the opposite of the derivative, so it's just not really an idea in and of itself. Again, the credit goes to limit, so the whole thing is really being done by limit. It's just, and the limit, as we discussed right now, it's a very simple idea, and therefore once you learn the idea of the limit, then it's calculus is not really any sort of complicated thing. It's a very simple thing. Okay, I guess I'm going to end this video here, and then we will continue with this in the next video. Thank you.